Good morning, everyone. Good morning, Logesh. Good morning, Yashuni. How are you? कैसे हैं आप लोग? Today we are going to start atomic physics. This is a very small chapter. Very basic things are here in this chapter. So let's do this. And I hope you have completed the dual nature. I think. What are the basic concepts in dual nature? I think you have covered everything in that chapter. Is my voice clear? Tell me once. Okay, very good. So now start. First of all, the first thing is in this chapter, what we deal with some atomic models. There were various models, various designs that were presented, but the thing starts with Rutherford's gold foil experiment. What is it? It's on your screen. What's happening here? Let's describe it in little bit of details. What I'm saying, this is a chamber of glass in which a radioactive substance is placed from which alpha particles are emitted. These alpha particles are striking on a gold foil. After striking, what we observe, this is a boundary, or you can say wall of something zinc sulfide. So what I'm saying, these alpha particles, what is observed that most of these alpha particles passes without any deviation. Without any deviation means they are going straight and just the gold foil is not affecting their path. But out of 8,000, on an average, 8,000 alpha particles, one alpha particle is returning back like this way. This is the alpha particle which is returning. So this indicates that the atom has a very heavy object inside it. What's the conclusion after this? That atom, there are basically two or three conclusions. What are those conclusions? One is the atom has a lot of free space. Only because of that, the alpha particles are going straight without any deviation in its path. But there is something very heavy inside the atom due to which the alpha particles are returning back. However, this heavy particle is taking a very less amount of space inside the atom. So what are the conclusions that you can draw from this? First conclusion, lot of space inside the nucleus. Second, the conclusion that we can draw is presence of very heavy particle in the atom. And this heavy particle was later termed as nucleus. What it was termed as nucleus. And it was again concluded that this nucleus has almost all the mass of the atom. I'm not writing this. This nucleus has almost all the mass of the atom and it is positively charged. It is positively charged. So these are the conclusions. After that, Rutherford proposed his model, and according to his model, what he suggested that in an atom, nucleus is at the center, and around which, in a circular orbit, electrons revolve. Electrons revolve in a circular orbit. This is the Rutherford's model, and I think every one of you are aware of that. After this Rutherford's experiment or gold foil experiment, he concluded one more thing, and that thing was the distance of closest approach, or you can say he estimated the size of the nucleus with this experiment. So there is one more statement that you should remember. After this gold foil experiment, he concluded two things. One is distance of closest approach, or you can say size of the nucleus. He estimated with this experiment. So remember this thing, that size of the nucleus was also determined by gold foil experiment. Now, what is the distance of closest approach? Let's suppose I am saying this is a nucleus. This is a nucleus which has some positive charge. Now, how can you determine that it has a positive charge ZE? Let's suppose an atom, there is a ZXA is a atom. Then number of protons in it are Z. If number of protons are Z and each proton has a positive charge E, so total charge will be ZE. And there is a alpha particle. This alpha particle is moving with some kinetic energy K alpha towards the nucleus. When it is moving towards the nucleus, this is positively charged nucleus, this is also positively charged. So there will be a repulsion. And at a certain distance before the nucleus, it just stops. So alpha particle stops here. So this is distance of closest approach. This distance is denoted by R naught. And what is the formula for this R naught? You need to remember it. This is an important relation. You need to remember that. What is it? 2 ke ZE square over K alpha. What is Ke? Ke is electrostatic constant, which is 1 upon 4 pi epsilon naught. K alpha is the kinetic energy of alpha particle. Z is the atomic number, or you can say number of protons in the nucleus. E is the charge of the proton, charge of one proton. So this is the distance of closest approach. Most of the times question may be asked from this. They may ask you the ratio of closest approach by giving the energy of alpha particles. You can clearly will be able to solve that problem. Ke, I think Logesh, I have mentioned this is electrostatic constant, which is 1 over 4 pi epsilon naught. Clear, Logesh? Okay. Now this E is charge of electron. Okay, very good. Moving further. So what are the conclusions for gold foil experiment? We have done that. Based on this gold foil experiment, Rutherford did two things. He made an atomic model. He showed a atomic model in which electrons were revolving in a circular orbit. But there were a lot of problems with that experiment, with that model, Rutherford model. So your task is to identify the problems in Rutherford model. This is a class 12th question and you should know that because it may be asked. Now moving further. Now comes Bohr. The problem with Rutherford model was eliminated by Bohr. What it says, listen, electrons revolve around the nucleus. Now listen to me very carefully. This is a nucleus around which electrons are revolving. I am explaining this. You can read the statements mentioned over here, but I am explaining it on side by side. Now, electrons are revolving in these orbits. So what Bohr says that electrons cannot revolve in any of the orbits. Mark my words, electrons cannot revolve and in any of the orbits. It revolves only in those orbits in which its angular momentum, which is L, is integral multiple. Integral multiple means N of integral multiple of H over 2 pi. This is what the most famous statement of Bohr. What is that? The angular momentum of an electron is quantized an integral multiple of H over 2 pi. That means electrons revolve only in those orbits in which its angular momentum is integral multiple of H over 2 pi, where H is what? Planck constant, N is an integer, L is angular momentum. So angular momentum can be written as mvr is equals to nh over 2 pi. This is the Bohr quantization rule. We will call it as Bohr quantization rule. Now, the Bohr says that in these orbits, electrons revolving are stable and they do not radiate any sort of energy. Mark my words. The electrons revolving in such orbits are stable and do not radiate any energy. Clear till now? So what are the Bohr postulates? One is they revolve in circular orbits. Another is they revolve in only those orbits in which its angular momentum is nh upon 2 pi. And these orbits are called as stable orbits. Are called as stable orbits. Clear? Moving further. Now, this is the next important thing. An electron might make a transition. You can read it out. I will explain it. Let's suppose this is a nucleus around which electrons are revolving in these orbits. So the thing is, in each of the orbit, it has some energy. E1, E2. Similarly, third orbit will have some energy, E3. That means in each of the orbit, electron has some energy. We can calculate that energy for hydrogen atom later, but the thing is, in each of the orbit, electron has some energy. And the statement says, if I draw these energies by horizontal lines or draw these orbits in horizontal line, then we can clearly see that, for example, this is first orbit having energy E1. This is second orbit having energy E2. This is third orbit having energy E3. I have drawn the orbits in a straight line path, nothing else, to represent the energy. Now, generally, electrons are in ground state. This is an electron. They are generally in ground state. Now, listen to my words. If some extra energy is given, then due to this energy, electrons may jump to some higher orbit. Electrons may jump to some higher orbit. It may jump to second orbit, it may jump to third orbit, or it may jump to any other further orbit. It can jump. One thing. When it can jump after receiving the energy, let's suppose it has reached orbit 3. Clear now? Now the thing is, in this orbit, it stays for a very short time. For a very short time means very, very short time. And after that, it returns back. After that, it returns back. While returning, there are various possibilities. While returning, there are various possibilities. So the thing is, listen to me in few sentences or one or two sentences. When electrons receive some external energy, it jumps to the higher orbit, where it stays for a very short time and returns back randomly. Randomly means if it jumps to the third orbit, it may jump to second and then to first, or it can directly jump to first. This is a simple possibility thing. What it will do, it cannot be determined. Now, in the process of returning, it releases a photon of energy. It releases a photon of energy, and this photon of energy has some energy because photons are what? They are packets of energy. So while returning, it releases a photon of energy, and this photon has some energy. I'm mentioning it here. This photon energy is given by the difference of the two orbits. The difference of the two orbits. That is, for example, this is transition 1, this is transition 2, this is transition 3. So energy is given by difference of the energies. That is E3 minus E1. Now, what is the conclusion? Electrons, when returns back, it releases some energy photon, and this photon has a energy equal to the difference of the two energy levels in which it is moving. For example, if I'm saying this is E1, this is E2, E3, and E4. Electrons are coming back from fourth to second. Let this is transition 1. Then what will be the energy of this photon released? What will be the energy of this photon? Can anyone answer? What will be the energy of this photon? It will be equals to the difference of energy levels. So what you say, energy of photon will be, EP is representing energy of photon will be the difference of the two levels from which it is starting E4, from which it is ending E2. So that will be E4 minus E2. Is this statement clear? Let's suppose if it is returning back from second orbit to first orbit, then what will be the energy of this photon? You will say energy of photon in the second case will be the energy level difference, that is E2 minus E1. Is this thing clear? If you say it is clear, only then I will move. Okay, very good. Now one more thing. I have told you that the electrons when returns back, the process is completely random. So what are the number of transitions that can be made? This is another very good question. Let's suppose electron is at, this is first state, this is nth orbit. So when it returns back from nth to 1, ultimately it will return to ground state. Ultimately it will return to ground state. So when it returns to ground state, how many possible transitions are there? So number of possible transitions, n minus 1 by 2. Remember, where n is the orbit in which electron is currently present and nothing else. Every term is same. For example, if electron is in fourth orbit, then how many possible transitions it can make? Answer quickly. How many possible transitions it can make from n equals to 4 to the ground state? You will say number of possible transitions are n minus 1 by 2. So n is what is, our electron is in the fourth orbit. 4 into 4 minus 1, 3 divided by 2. That is 6 transitions. Very good, 6. Very good. I think it's clear now. So Bohr model, one is Bohr quantization rule, another is this transition thing. These two things are important in Bohr postulates. Now moving further. Now there are some formulas that you should remember. I can't help you in that, but I will tell you one thing, what you should remember. This is the actual formula. What's happening here? This is a hydrogen-like atom. they are talking about. Hydrogen-like atom means one electron atoms. The atoms in which there is only one electron. For example, one is hydrogen, which has one electron. Can you say that helium has two electrons? But if I remove one electron, it will become helium plus. So helium plus also have one electron in it. Similarly, lithium double plus also has one electron in it. Can you see this now? Similarly, you can say beryllium triple plus is also a hydrogen-like atom. So this theory, the formula I am mentioning here are all valid for hydrogen-like atoms in which there is only one electron. Now, let's suppose this is a hydrogen-like atom. This is the nucleus which has charge Ze, and an electron is revolving in a circular orbit of radius r with some velocity v. Then its velocity v will be given as, the formula is on your screen, Ze square 2 epsilon naught nh. You can remember this relation. There is nothing wrong. You are going to be participants of a competitive exam, so you can remember this relation. Next is, if I place all these values, out of which you can see epsilon naught is a constant, h is a constant, charge of electron is a constant, 2 is a constant. So if I place all such values, it comes out to be 2.2 into 10 raised to the power 6 Z by n. Z by n, where n is the number of orbit, or it is generally called as principal quantum number. Quantum number. This is something chemistry thing, but you can remember. Now, what is Z? Z is the atomic number. For hydrogen atom, Z is 1. For helium atom, Z is 2. Lithium, Z is 3. Beryllium, Z is 4. So Z is what? Atomic number. Clear? N is the number of orbit or principal quantum number. So if I ask you, what is the speed in first orbit for hydrogen atom? Can anyone answer? What is the speed of electron in first orbit for hydrogen atom? Can you clearly see that for hydrogen atom, Z is 1, N is also 1 given. So V is equals to 2.2 into 10 raised to the power 6 meter per second. Now, one important thing that I can draw your attention for, if I talk about second orbit, can you see that V is reciprocal to N? V is reciprocal to N. That means its speed will decrease. So what I am saying, if N increases, then speed decreases. This thing is very important to remember. Various times it is asked directly. So either you can remember this relation or you can remember this thing, that if N increases, velocity or speed of the electron revolving decreases. Clear? हिंदी में बोले तो जितना पास होगा उतना तेज इलेक्ट्रॉन रिवॉल्व कर रहा होगा. Electron will be revolving faster in nearer orbits, which are closer to the nucleus. Moving further. Now there comes a radius. This radius r is given as n square h square epsilon naught pi m z e square. In all these relation, m is the mass of the electron. H, Planck constant, epsilon naught pi m z e square. Out of this, you can see that h square epsilon naught pi m z. Sorry, pi m and e square, everything is constant. And for hydrogen atom, if I talk about, at n equals to 1, if I talk about for hydrogen atom only, and for n equals to 1, this R comes out to be 0.53 angstrom. This is actual value 0.53 angstrom. That means hydrogen atom has first orbit of radius 0.53 angstrom, which is very small. And this radius is called as, everyone knows that this radius is called as Bohr radius. So if someone asks you what is Bohr radius, listen my words, what is Bohr radius? Bohr radius is the radius of first orbit of hydrogen atom. Radius of first orbit of hydrogen atom. And it is generally denoted by R naught. Generally denoted by R naught. Now, radius of any other orbit or any other atom can be written as this way. R is equals to R naught n square by Z. R naught n square by Z. First orbit has a radius 0.53 angstrom. Then second orbit has a radius of 4 times of R naught. Can you see that n is equals to 2? If you put, it will become 4 R naught. N equals to 3. If you put, it will become 9 R naught. So you can get radius of any orbit of hydrogen atom or any other atom using this relation. Very simple relation. Important. Remember this relation. Next comes time period. Relation is on your screen. Out of this, I think this should be remembered. On which it depends. It is directly proportional to n cube and reciprocal to z square. This thing is important, nothing else. You can remember this thing only. Now, there comes a very important relation, energy. The energy of the electron in any orbit. You can remember this relation, but the most important relation is this one. Minus 13.6 z square by n square. This energy is in electron volt. Write it down on your notebook so that you can revise every time. The minus sign indicates, I told you, attraction or bound system. Bound means with the bodies which are bounded by attractive forces. So electrons are bounded with the nucleus. That's why energy is coming as negative. Now, another thing that is to be remembered and very important is this relation. Energy of the atom is mainly due to two factors. One is kinetic energy and one is potential energy. Total energy is given by two factors. One is kinetic, one is potential. So the relation between these three quantities is on your screen. What it says, kinetic energy is negative of total energy. For example, if I say that total energy is minus 3.4 electron volt, then the kinetic energy will be 3.4 electron volt. Can you see this? That kinetic energy is equals to potential, so equals to total energy, but with negative sign. Next relation is potential energy is equals to 2 times of kinetic energy with negative sign again. Potential energy is what? 2 times of kinetic energy. And next is potential energy is 2 times of total energy. You should remember these relations. Moving further. Hydrogen spectrum. I told you that after receiving energy, electrons jumps to the higher orbits. The first orbit is generally known as ground state. Remember this word, you will be confused otherwise. This is known as ground state. And after that, n equals to 2 is known as first excited state. This is known as second excited state. What does it mean if someone asks you fourth excited state? What does it mean? Fourth excited state means what is the value of n? What will be the value of n for fourth excited state? 5. Very good, Logesh. Very good. Very good, Chichuni. Now, when these electrons returns back, based on that, there are some series mentioned. Now listen to me very carefully. Whenever the electrons returns to the ground state, all these electrons you can see they are returning to the ground state from infinity to ground state, from n equals to 6 to ground state. So every electron is returning to the ground state. Now, one more thing you can remember from this diagram, the energy levels of hydrogen atom. For n equals to 1, energy is minus 13.6. For n equals to 2, energy is minus 3.4. I think up to n equals to 5, you can remember or you should remember. Up to n equals to 5, you should remember. This is your task to remember the energy levels or energies up to n equals to 5. When electrons return to the ground state, it is termed as Lyman series. Similarly, Balmer, when returns to the second orbit, when returns to the third orbit, it is known as Paschen series, bracket P-Fund. P-Fund में P generally is silent, so it is called as Fund series. I think you have studied that in chemistry as well, in physics as well, so I'm not taking a lot of time. I'm telling you the important things here. When electrons return to the second state, it is Balmer series. Out of these series, all these transitions releases some photon, and photon has some energy, and this series lies in the ultraviolet region. This series lies in the visible region, and all other are lying in the infrared region. This is again an important thing you should remember. In which region they lie. One more thing after that. That is very important to understand. The first line of any series is the closest line. Can you see that? This is the first line of Balmer series, second line of Balmer series, and this is the last line of Balmer series. Similarly, Paschen series, this is the first line, second line, and this is the last line of Paschen series. Clear? The first line of Balmer series is called as H alpha. Second is known as H beta. Third is known as H gamma. This is a common term that generally used as first is known as H alpha, second H beta, third H gamma. So whenever they are talking about H beta line, that means you should clearly understand that electrons are making transition in Balmer series from, or you can say second transition of Balmer series, that is from fourth to second orbit. Similarly, things can go. Moving further. Now, one more thing. If I write here, I think it will be visible. Okay. I am talking about for Lyman series. For Lyman series. There is one more question that generally can be asked. There are two wavelengths that they ask. One is shortest wavelength, another is longest wavelength in a transition or in a series. Listen to my words. The question may ask you longest wavelength of a transition and shortest wavelength of a transition. Simple question. Now, in a series, if I talk about, there are various transitions like this, various transitions. Energy of photon in any of the transition is calculated as the difference of the two levels. And energy of photon is generally as hc by lambda. Energy of photon we have studied in the previous class, which is hc by lambda. So lambda is equals to hc by delta E. Clear? So if delta E is smaller, then lambda will be larger. Now answer me, for Lyman series, which line will have larger wavelength? Which line will have larger wavelength? This is the first line, second line, third line, and this is the last line. So which line will have larger wavelength or largest wavelength for Lyman series? Last line. Lokesh is saying last line. Anyone else? Gauri, you are not answering. Darshana, Ritu, do you get the question? Question is saying that lambda is reciprocal to delta E. Delta E is the energy difference of the two levels. Gauri Lakshmi is saying second. Okay. Okay. Now listen. Very good, Gauri Lakshmi. You are saying from n equals to 2 to 1, na? That's what you are saying, Gauri. That means first line you are talking, na? Okay, very good, Gauri. So I will tell you a basic punchline so that you can remember. For longest wavelength, the transition you understand, na? The transition means movement of electron. The transition should be nearest. What does it mean? The transition should be nearest means if transition is nearest, the energy difference will be smaller. Energy difference is smaller, than lambda will be largest. So you can remember this punchline: for largest wavelength, transition should be nearest. And opposite to that is for smallest wavelength, the transition should be longest. If I talk about, let's suppose Balmer series, and if I want lambda maximum, then transition should be from which orbit to which orbit? Transition I am talking about, from which orbit to which orbit, there should be a transition for maximum lambda in Balmer series. Be quick in responding. Chichuni says 5 to 1. Okay. Anyone else? Logesh? Do you understand what is the meaning of nearest transition? Okay, very good. Not very good. Chichuni, again, there is a mistake. I am talking about Balmer series. Now, Balmer series, if you can see that in Balmer series, all the electrons are returning back to which orbit? Only to the second orbit. Nothing is coming back to the first orbit. So one thing is clear, electron should return to second orbit. That means final is second orbit. And for nearest transition, it should come from third to second. It should come from third to second. Is the point clear? Balmer series, electrons are returning back to second orbit, not beyond that. In the Paschen series, electrons are returning back to third orbit only. So for longest wavelength, what it should be? From fourth to 1, that is first line. For bracket series, longest wavelength will be 5 to 4. This is lambda max. This is lambda max. That means first line of every series is the longest wavelength. And the last line of every series is the smallest wavelength. Now I think point is clear. Moving further. There is a formula for calculating the wavelength in terms of Rydberg constant. Listen, again, very careful. This is the most important relation for calculating the wavelength. Very good, Veena. Very good. Now, using Rydberg constant, what you can conclude that, let's suppose an electron is some higher orbit N2. I am not saying this is N equals to 2. This is N2 means any orbit. And this is the ground. This is another lower orbit N1. Electron is making transition from higher orbit to lower orbit. In this process, a photon is released and the wavelength of this emitted energy of this emitted photon is given as 1 by lambda is equals to Rz square 1 by N1 square minus 1 by N2 square. So most of the times you will get confused. So this N1 is representing lower orbit and this is representing higher orbit. Where R is the Rydberg constant, Z is the atomic number, lambda is the wavelength. And this 1 over lambda completely is called as wave number. So sometimes question may ask you not wavelength, but the wave number. So wave number is generally 1 by lambda is itself called as wave number. Now there is a time of some questions. Let's try to solve it out. Write this formula so that we can easily do this. Clear? Question. Now we have some time of 15 minutes so that we can, or you can solve the question. You can solve the question. The question says the ratio of wavelengths of the last line of Balmer series and the last line of Lyman series is. Whenever we talk about the last line, that means transition starting from first orbit. Now there were two series. One is Balmer and another is Lyman. That's what they are talking about. And they are talking about Balmer series. If I say last line, remember one thing, Balmer series electrons returns to second orbit. Last line means from infinity to second. In Lyman series, electrons returns to first orbit. This is a surety. Lyman series electrons are returning to first orbit. From which they are saying last line. Last line means from infinity. That means you are able to understand that what is the meaning of the statement. Now we need to calculate the wavelength. Now let's suppose for Balmer series I am talking. If I write 1 by lambda 1 is equals to, what is the formula? Rz square 1 by N1 square minus 1 by N2 square. N1 was the lower orbit. Option B, someone is saying, I think who is saying? Gauri. Very good. Let's check it. N1 is the lower orbit. That means that is square. If I square, that is 4. Minus if you see infinity square, that will be 1 by infinity is 0. Or you can say lambda 1 is equals to 4 upon Rz square. Equation number 1. And now for Lyman series. For Lyman series, again, if I say 1 by lambda 2 is equals to Rz square, lower orbit square, that is 1 minus 0. Why 0? Because infinity, 1 by infinity means 0. So what it will be? Lambda 2 is becoming 1 by Rz square. Now we need to calculate the ratio of lambda 1 by lambda 2. That will be 4. Very good. Very good, Gauri. Okay, Jismi, just wait. Look at the Balmer series. Have a look at that. In this equation, in this diagram, you can clearly see that whenever someone is talking about Balmer series, you can see these are the transitions. In Balmer series, you can clearly see no electron is moving below the n equals to 2. That means electrons are ultimately coming to n equals to 2. They are coming to first excited state or the second orbit. They are coming from third orbit to second, fourth to second, fifth to second, and from infinity to second orbit. When they are returning to the second orbit, that means ultimately the final orbit is the second orbit. One thing is clear. And the last line means from infinity to second orbit. Last line means from infinity to second orbit. Clear? In Lyman series, electrons returns to the first orbit. That's the surety. That's why it is called as Lyman series. Returning to the first orbit. But last line means returning from where? From infinity to first orbit. That's what we did. Okay. So moving further to the next question. I think this question is clear now. Very good. Now this is again a very simple question. The formula based question also asked in PYQs. All the questions were of PYQ. The total energy of an electron in an atom is minus 3.4. So total energy is given as minus 3.4 electron volt. Its kinetic energy and potential energy are asked. So we know the relation kinetic energy is equal to negative of total energy. That's what the golden punchline, golden box. Veena, can you answer what will be the correct answer for this question? So kinetic energy will be plus 3.4 electron volt. Is it clear? Minus and minus will be cancelled now. So it will be plus 3.4 electron volt. Now what is the potential energy? U is equals to minus 2 times of kinetic energy. Gauri is saying D option. So U will be minus, if you see 2 times of this 3.4, that will be 6.8 electron volt. Very good to answer. Logesh is also saying D. Chichuni is also saying D. I think Veena is also saying D. That means everyone got this question. Very easy. Moving further. Now, this is another question. Try to solve it out. I am waiting for a response in this question as well. If an electron in a hydrogen atom jumps from third orbit to the second orbit, it emits a photon of wavelength lambda. Clear. When it jumps from the fourth orbit to the third orbit, the corresponding wavelength of photon will be. Now, this is very interesting thing. Which formula you should use? I think Rydberg formula that comes to our mind whenever there is a transition, orbits are given third to second, fourth to second, whatever is given. Okay, so Rydberg formula we are going to use here. So what is it? So first statement is third to second orbit. Let's suppose wavelength is lambda 1. So 1 by lambda 1 is equals to RZ square. Now 1 by lower orbit square, that is 4 minus 1 by 9. If you take the LCM, it will become 36. And 9 minus 4, that is 5 RZ square. That is 1 by lambda 1. Or you can see that lambda 1 will be 36 by 5 RZ square. This is lambda 1. Now let's talk about second transition. Second transition is from fourth to third. Fourth to third. Now we can write as 1 by lambda 2 is equals to, again, RZ square. Try to solve it in parallel with me. And let's see who will win. Okay. Chichunu is saying C. Very good. You are doing great job here. So What was that? 1 by 9 minus 1 by 16. That will be 144, 7. I am taking just LCM thing, na? RZ square. So lambda 2 will be 144 by 7 RZ square. So if I divide these equations, so lambda 2 by lambda 1 will be 144 by 7 RZ square into 5 RZ square by 36. You can divide these things, RZ square. I think you can clearly see that 12, it will be cancelled. 12, 12, 3, 3, 4, 4, that is 20 by 7. The ratio is 20 by 7, so lambda 2 will be 20 by 7 lambda. That's what is the answer. I think which is option number C. So that's very good. First, Veena is also great, doing great job here. Very good, Veena. So there is one more type of question that we are going to discuss. Logesh, is this question clear? Have you solved it, or you are facing some difficulty in that? Very good. So moving further on the next question. Read out the question first. Okay. Question says, hydrogen atom in ground state is excited by a monochromatic radiation of wavelength 975 angstrom. Okay. This is the electron in ground state, n equals to 1. And the electron is there. There is the electron. Some extra energy is given to it. And this extra radiation has a wavelength of 975 angstrom. 975 angstrom. So if I solve this, what will be the energy of this radiation? You will say E is equals to Hc by lambda. I'm not going to calculate this thing. I am giving you an idea. So I can use the calculator here for the calculation. And if I use the calculator, because it will take a lot of time, that will be around 12.75 electron volt. That means the energy which is coming on the electron or coming to the hydrogen atom in the ground state is 12.75 approximately electron volt. You know the value of Hc and lambda is also given, so I have calculated this value. Now, in ground state, hydrogen atom already has some energy, that is minus 13.6 electron volt. Very good. Not 975. 975 is in angstrom. So you have to put 97.5. I told you, not convert it into nanometer. So for converting it into nanometer, you have to shift the decimal by 1 point. Clear? So now if I say 13.6 electron volt is the energy in the ground state, and you have given approximately 12.75 electron volt to it. Electron already has this much of energy and you have given extra energy. So the total energy of electron will be total energy of electron will be, it already has minus 13.6 electron volt and you have given 12.75 extra. So if you subtract these two values, what you will get 15 less than, that is minus 0.85 electron volt. That's what you got. I think clear. This is the remaining energy of the electron. Now, what will happen? You can see that if you can see after receiving this energy, this 12.75 energy, electron will jump to some higher orbit. Let's suppose it has jumped to nth orbit. It has jumped to nth orbit. Till now, every point is clear what I did here. It has jumped to nth orbit. Now, in nth orbit, its energy is given as energy in nth orbit is given as minus 13.6 n square. Let me remove something. Minus 13.6. Where is the eraser? Z square by n square. This is the energy in the nth orbit we have studied in the energy formula. So now, what will be the value of n square? N square will be, Z is a 1 for a hydrogen atom that it can be removed. That is minus 13.6 divided by energy. So energy that we have calculated is 0.85. So put the values minus 13.6 divided by 0.85 minus. Now we have to again calculate it using calculator. I am using calculator. It is not recommended for you to use calculator. That comes out to be 16. So n square is coming out to be 16. That means n is coming out to be 4. What does it mean? After receiving that radiation, electron jumps to the n equals to 4. So question is saying or asking number of spectral lines in the resulting spectrum. Number of spectral lines means number of transitions. How many transitions it can make. So from n equals to 4, if it is returning, then how many transitions it can make? There is a golden formula I have told you. Number of transitions are n minus 1 by 2. So put the value of n equals to 4 and you will get the answer. Now put the values. What you will get? That is 6. 6. Very good. So which option is correct here? 6 is correct. Now this is very important question. C. Very good, Gauri. This is very important question. Can you understand what's happening here? Whenever the electron receives some energy, so first of all, you need to calculate the total energy of the electron. This total energy of the electron, after calculating this, what you need to do? Let's assume that electron has jumped to nth orbit, and in nth orbit, its energy will be something like that. Clear? So get the value of n, and you will get the answer. So I think time is also over. I am ending the class. Bye, everyone. Yes, I am in JNV Pondi, Logesh. How you know? How you come to know about that, Logesh? JNV Pondi? What's Logesh? Okay. So you are in class 12th right now, or have you are passed out? Okay, very good. Okay, so right now I am ending the session. Bye, everyone.